I want to show you how easy it is to believe in perpetual motion machines. And I'm going to tell you about two machines to make the point that it's easy to believe in perpetual motion machines, or to half believe in them. I'll tell you about my experience. Years ago when I was a kid and had to go to Sunday school, my father would take me to Sunday school, and he knew I didn't like it, so he would usually tell me something interesting on the way back. And he told me one time that the world was running out of oil, and that if there was no oil, there'd be no gasoline, and then we wouldn't be able to drive the car anymore. Incidentally, this was way back in the 1940s that he told me that. And that troubled me a bit, that we couldn't drive the car. So I made an invention as a very young kid that would make the car go without the use of gasoline. And I'd like you to tell me what's wrong with this, or maybe it'll work. Who knows? Here's the idea: that it was a wagon, like so, and there's the wagon, and there's a guy inside the wagon, and you have a long pole out there, fishing pole, and on the fishing pole there is a magnet. And of course the magnet attracts the car. And then of course the car moves a little bit, then the magnet will go off, this fellow will be moved, and then the pole will be moved, and you see the thing will keep on going forever. It's sort of like the carrot in front of the horse. Of course, you know it won't work. But the question is, why won't it work? Why won't it work? How do you show this? Now, there's various ways you might say. You could just say, well, a perpetual motion is impossible. That's not an adequate explanation of why it won't work. Because it doesn't give the reason. You might say that for every force there's an equal and opposite reaction, which is also correct, but it still doesn't show the reason why the thing won't work. Of course, maybe it will work, but if it will work, how could you make it work better? You know, I'll show you a way that you could make it work even better. What does a magnet attract better even than metal, than iron? What a magnet attracts better than iron is another magnet. So let's improve this thing, and I'll tell you how we'll improve it. This is the first improvement here. What you do here is you take this off, and here you put put another magnet out here like that. There's another magnet. And see, then maybe you'd still need this pole here, but see if that thing would. See that version ought to work even better. But of course, if Chrysler were to make this thing, it'd look kind of corny having a magnet sticking out in front there. So you can kind of get the whole thing under the hood, inside the engine, in the following way. I'll show you how you could kind of streamline the thing, and it would work look better. Be the same principle, but at least it looks better this way. Make it like this, you see, and put on wheels like that. You see, and then I could sit up here. There's a guy, smaller guy. See, now it's nice and clean. But now you can also see what's wrong with it. And we've used here a principle that's used over and over again in physics, sometimes in a very sophisticated way. Here we've used it in a very crude way. We can see that the thing is symmetrical. It's the same on both sides. And so the question that you immediately have when you have a thing like this is, which way will it go? And automatically you see that whatever force one magnet exerts on the other magnet's going to exert back. So there it is. There it is. This machine won't work. But you think, well, I'll show you another idea for a perpetual motion machine. If this one won't work, maybe another scheme will. Now, years ago, also when I was a kid, my sister had a little plastic ball. It was a hollow plastic ball, maybe 2-3 inches in diameter. It was the most amazing ball. When you put it down underneath the water, and this is some water, and when you put it down underneath the water, it would come up, as most balls will. It was full of air, a plastic ball full of air, but it would come up so fast, and it was so smooth on the outside that when it came up, it would actually jump out of the water. Not far, but it would jump up maybe 6 inches. It jumped up quite a ways out of the water before it fell back. And therein came another idea for a perpetual motion machine. And I'll show you the second idea for a perpetual motion machine. Let's see if we can see what's wrong with this one, or maybe nothing's wrong with it. Maybe it will indeed work. You start with a long pipe, and this pipe is full of water. This pipe is full of water all the way down to the bottom. And here you put in a ball down at the bottom, namely my sister's plastic ball, and it will rise up faster and faster and faster till it gets to the surface of the water, and it will jump out. But up here you put something, you put a little thing like this at an angle so that when it hits this, it bounces, and the ball goes over here. And then the ball falls into a tube, and here's a long tube, and the ball will fall right back down again. Hit this tube, and it will go right down, 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 down to here. Now, you have to get the ball back from here over to here. Of course, the ball isn't here anymore, so we have to get it. We have to get it. So take the ball over here, and in here we have one of those airlocks like Jacques Cousteau has, you see, and so the ball can go back into here. As soon as it gets in the water, then it floats up to the top of the water, jumps out of the top, hits the top, comes over here, goes down here, then goes through the airlock again. You see, and it can go around and around and around. What's wrong with that scheme? Well, we have to think a little bit about how you get back in the water. How does an airlock work? Well, an airlock works this way. It's a thing that has 2 doors on it. So first of all, here's the 2 doors, and the ball comes down here, and you first leave this door closed and you open this door. Okay, then the ball can roll in. Like we'll kind of bevel this thing here. So this thing comes right down here. This door opens and the ball rolls in. Then this door closes behind it, and then this door opens. And when this door opens, the water comes in here, and this ball can come out. And it comes out, comes back up, hits here, jumps over and comes back over, comes here again, but now this thing is all full of water. And you'd have to empty the air, you'd have to empty the water that is now filling the airlock. The airlock is now filled with water, and you'd have to get it out of here. To get it out of here, you'd have to get it back up to the surface there. It's a long ways up. You'd have to do a lot of work to get it back up to the surface. And so this thing would work. It would work okay, but it would only work for one trip. You could conceivably make one trip with it, and then it couldn't work anymore. So it would not be a source of perpetual motion. You see, the ball here has to enter the water at the bottom, and water down deep is under pressure. And so when you enter water that's under pressure, you have to push the water that's in front of you out of the way, and that takes work, and that's why this scheme won't work. Of course, if this scheme won't work and the magnet car won't work, who knows? That was the thought of a 11-year-old kid. So with a couple more years of physics, you might be able to think of something that will work. We'll see. We'll see. You know, there's no proof that a perpetual motion machine will not work. And in geometry, you can prove things. In physics, you cannot. The only reason, ultimately, that we know that perpetual motion will not work is that after 4,000 or 5,000 years of people trying, no one has succeeded. That's the real way that we know that the thing won't work. Well, we're going to talk some more about levers and machines today. And the reason for talking about these levers and machines is not that each of the things is kind of clever and interesting in and of itself, but the main point is I'm trying to illustrate the principle of work. And so the things that you're going to see in the course of my examples, you might call them all levers of one kind or another. You know, it says in the Bible that the devil has many guises. And I think you're going to see in today's talk that the lever has many guises. Let let me begin with a few examples of the idea. Let's take, here's a wall of a house, or at least this is the blueprint of the wall of a house, and we'll put a door in the wall. There's a door opening, and there's the opening for the door. And now let me open the door a little bit, and there's the door ajar, and there's a hinge, and there it is, and there we put a doorknob there and a doorknob there, and there's the blueprint of an open door in the house with a doorknob on each end, a little bit ajar. And of course, now there's one place where you wouldn't want to put your finger when you have a door. You wouldn't want to put your finger in here, isn't that right? Because you stick your finger in there, it's going to hurt. That's where but let's do a little calculation. How much force can be in the door jamb? Now, something else you can do, you can use the door jamb as a nutcracker, particularly if you don't own the house and you're renting it from a landlord. You can put the nut in the door jamb. And okay. And, now, how much force is exerted on that nut that's in the door jamb there? Well, let's look at it. Let's pretend that when the door closes, the jamb is going to close 1 inch. So 1 inch. That's how much the jamb is going to close. Now, how much does the door move? Of course, you're pushing here on the knob. That's where you're pushing on the door. How far does that go? Well, let's pretend that to close the door, that this thing is going to close. It's not going to go 1 inch. This is going to go, let's pretend this is 1 foot. 1 foot to close the door, and the jamb closes 1 inch. Well, where's the big force? On the door, or is the big force in the jamb? Well, from experience, you know the jamb is the place where the big force is. That's where you'd put the walnut if you wanted to break it. And of course, the reason why is that here's a machine. When one end moves a lot, namely 1 foot, the other end of this machine moves a little, namely 1 inch. In fact, we even know the ratio of the motions is 12 to 1 because there's 12 inches in a foot. So this motion here is only 1/12, or this is 12 times as great. And so the force is going to be in the same ratio, which means the force here is going to be 12 times as great. However much force you can push on that door, and let's say you can push on it with 100 pounds, well, then there's going to be 1,200 pounds of force on the walnut. So that's a pretty effective walnut cracker. And if it doesn't crack the walnut, it'll break up the landlord's door anyway. So there you go. So let me show you something else, another situation. I want you to analyze this problem here. This is a typical problem here. I want to have here here is a shaft, and then turning on the shaft are 2 wheels, and we'll have 1 wheel here. There's 1 wheel, and then here's the wheel, and then solidly attached to that wheel is another wheel here. And there's the second wheel, and there's the shaft. Now, if you were to look at this end on over here, this way, the thing would look like this. It'd be a shaft, and then there'd be a wheel here like this, and a second wheel out like that. Yeah, that's what an end view of the thing would look like. And of course the shaft, well, I like the shaft go right through the whole thing, so the whole thing can turn on the shaft, right? And if you were to look at it this way, well, let's see what it would look like this way if you were to look at it. Here would be the big wheel, and here would be the wheel that's half the diameter, and there would be the shaft right inside. Okay, now these 2 wheels are made of one solid piece of wood or metal. That means that when this one turns once, the big one has to turn once. They're rigidly hooked together. They're glued together. They can turn on their shaft, but they turn together. Now, I want to wrap a string around here and finally hang a weight from the string. And here's this weight, and this weight is, what should this be? Well, we'll use my favorite number. It's a 1 pound weight. In other words, from here we hang down a 1 pound weight. And from here we hang down a 1 pound weight. Now, of course, if this 1 pound weight just hung here and the string was wrapped around, of course, it would begin to pull, and the wheel would begin to spin and spin and spin and spin, and the thing would spin up. But I don't want it to move. I don't want it to spin. So I'm going to wrap another string around this wheel here a couple times, wrap it around, and then let the string come down here. And I'm going to attach another weight over here. Now this is a weight is an unknown, X. Of course, if this weight X were here and 1, this wasn't here, then this would make the wheel spin the other way. It wants to make the wheel spin the other way. Here's the other weight hanging down here. This is weight X, and here you can see it here. It hangs down the other side. This is X. Okay, now, so my question to you is, what should X be? Well, right away you see that these wheels have a ratio of 2 to 1, and you get a feeling that, well, maybe X should be 2 pounds, or maybe X should be half a pound. But which should it be? How can we analyze this thing? Okay, we'll analyze it again according to the principle of work. Now let's pretend that we have enough string here. These go down far enough. And let's pretend that the wheel makes 1 turn, 1 complete revolution. Then as it goes around this way, string is going to come off the wheel. If the wheel makes 1 turn for the 1 pound weight, how much string is going to come off the wheel? Well, one whole circumference of string is going to come off. And so this thing is going to go down a certain distance, which is equal to the circumference of the big wheel. Now, at the same time that this 1 pound weight is going down, X is coming up. How far is X going to come up? Well, if the big wheel makes 1 turn, then 1 wrap of the string is going to come off the big wheel, and this one is going to suck up string. How much string is it going to suck up? Well, it's going to suck up enough to go wrapping around the little wheel. That's how much it's going to suck up. So the little weight is going to move a certain distance upward, equal to the circumference of the little wheel. And now, what are these 2 circumferences the same? No. What's the ratio? The ratio is 2 to 1. We know the ratio is 2 to 1. So we know that every time the 1 pound weight moves a certain distance, the weight X is going to move half that distance. Now, if we want the work that goes out here to equal the work that has to come in here, and by the way, what goes out here will come in here. How do I know that? Because these weights always move in opposite directions. If we want these things to balance, and this one only moves, X only moves half as far as the 1 pound, this one has the small motion. If it has the small motion, it must have the large force. How can it have the large force? By weighing twice as much. It has to weigh twice as much. So X has to be 2 pounds to balance in this situation. And then it will balance. Now what we have here is this is a simple gear system. This story of pulleys and gears is repeated over and over again in machines. In fact, it's the whole idea of the bicycle. The wheel turns on one radius and you pedal on another radius, and you change the force. These things seem kind of strange. It's nice to see that hidden in this thing is a lever. And I'd like you to show you that hidden inside of this thing is a simple lever. Let's take this picture right here. Let's take this picture. And of course, this weight could be attached. We could just put a pin here. We could just put a pin in here and the 2 would balance if this was 2 to 1. Now, this top part of the wheel, is it doing any good? No, it's just up there for the ride. It's not doing anything. So I could take a knife and cut it off. And this bottom part of the wheel, is it doing anything? No. If the wheel isn't turning, it isn't doing anything, so I could take a knife and cut it off. And then I'd have a thing like this. And then you could say, is this little piece out here doing any good? No, because the thing is pinned here, so I can cut this off. And this is the pivot here. And look what you got here. There's a little lever, and the distance from here to here this is the short end, 1, and this is the long end, 2. So it's a little in there, hidden down inside that gearing is nothing but a 2-to-1 lever. So the lever, as I said, has many guises, and here is one of its guises. Now I'm going to show you. I'm going to show you. So far, these levers actually did. They were levers. They were kind of disguised levers. But now I'm going to disguise them really good, so you'll never even be able to find a lever in the thing. I'm going to show you another problem. The problem of the inclined plane. And here it is. Now, here's the back end of a truck. And here's a barrel. And this barrel is down on the ground. And maybe it's a 100-pound barrel. And here's a stevedore. And this stevedore can lift the barrel up and put it up on the truck. That'd be quite a job, but the stevedore can do it and can lift the barrel up there, and of course it's a 100-pound barrel. Okay. And let's say there's a certain distance up to the truck. I don't know what the distance up to the truck is, but let's say it's 3 feet up to the truck, and it's a 100-pound barrel. How much force does the stevedore have to use to get the barrel up there? Well, a lot of people will say, well, gee, let me analyze this. It's work. Force times distance, 100 pounds times 3 feet. But of course, no, that wasn't it at all. I asked, how much force does the stevedore have to use to get it up there? And the answer is 100 pounds, because it was a 100-pound barrel. Here's where knowing a little physics is dangerous. See, it's a 100-pound barrel, so you have to use 100 pounds of force. Now, there's another thing you can do. You can go and you can get a ramp, and you can get a ramp. And let's suppose you get a 12-foot ramp. Yeah, I don't know if this looks like a 12-foot ramp, but pretend it's a 12-foot ramp. We'll pretend this ramp is 12 feet long, and make sure that see that 12 feet long. And now, instead of lifting it up, the stevedore can do the following thing. It can push it up the ramp. Now, it's still 100 pounds. How much force does the stevedore have to use to roll it up that ramp? Well, I say, well, still 100 pounds. It's a 100-pound barrel. Well, of course it's not 100 pounds. You wouldn't have gone through all the trouble of setting up the ramp if it would still be 100 pounds. What would be the good of buying a ramp and setting it up if the force is 100 pounds? It's something less than 100 pounds. Now, the usual way to analyze this, if you were to take this problem and try to get help from a physics student, and I was to give it to you for homework, and you said, well, I'm going to go talk to a physics student about how to solve it. The physics student would say, well, there is a thing called a vector coming down, a force vector, and this vector has a certain component that pushes into the ramp, and then a certain force that pushes backwards, and then you take sines and cosines to find these components. But of course, we're not physics majors, so we can't do that. So I don't know anything about that. That's too complicated for me. So that's where that whole idea is just beyond me. So leave it alone and forget it. So let's come back to the real problem. Now, there's two ways a stevedore can get the thing up there. He can either lift it up or he can roll it up. In which case does he do more work? Does he do more work by lifting it up or by rolling it up? Well, you can answer that question by taking the work back out. How do you take the work back out? Well, you can kick the thing off, and it'll come down here and it'll hit the ground, and the barrel will burst with a huge bang. Which way will it make a bigger bang? If you lift it up and then throw it off, or if you roll it up and then throw it off, will it make a bigger bang? The answer is don't be stupid. It'll make the same bang either way, which means that the work that you put into getting it up there was the same, because it's that work coming out that makes the bang when you throw it off the truck. So the work going up this ramp is the same as the work going up here. And now we're on the road to the answer. Because the work is equal to the force times the distance. Now here, the work? What is 12? 12. I'll tell you at 12, I learned something what 12 is. 12 is equal to 3 times 4 is 12. And this is just 3 over here. So this ramp is longer than lifting it up. How much longer is this ramp than lifting it up? It's 4 times longer. He pushes it 4 times as far. He pushes it 4 times as far and does the same work. How can he push it 4 times as far and do the same work? He pushes it 4 times as far and does the same work because the force that he pushes against is only 1/4 of the weight of the barrel. The barrel's 100 pounds. 1/4 of that is 25 pounds. And so he pushes here with 25 pounds of force. 25 pounds pushing 12 feet is the same as 100 pounds pushing 3 feet. But in both cases, you do the same amount of work. Here, he has a huge strain on him, but for a short distance. And here, he has a much smaller strain, but for a longer distance. Now, for human reasons, this is easier because what kills, what breaks a person's back is not really the amount of work they do, but the amount of strain or force that's put on them. And so if you can minimize the strain, a person can do the heck of a lot of work. And that's the idea of the ramp. So here, this too is working exactly on the principle of the lever, though of course you can't see any lever there. Once we understand that, I'll show you some more things. There's something that appears over and over again in the world, and it's the screw. Sometimes you use in the olden days, and still when you're lifting up a house, there's house jacks, and they have huge screws in them. Some nutcrackers have screws in them where you exert enormous force on the nut by turning a screw. And I'm sure you've all seen book presses or wine presses where you turn a screw and you put quite an enormous amount of force, much more force than you're putting here, coming here. Let's analyze the screw. Turns out that I have here here's a screw, and here's a screw, and I'm going to turn the screw, and look, as I turn the screw, the thing moves forward, and I'm squeezing something, and while I'm not putting out very much force here with my hand, nonetheless at this end here, there's probably some very large force that's coming out. So a screw is something that allows you to put out a little bit of force and have a lot of force exerted on something. What's the principle by which a screw works? Well, I'll show you here. Here's the principle by which the screw works. And you can see what a screw is. A screw is nothing but an inclined plane, all wound up. That's what a screw is. It's another way of analyzing exactly the problem that I have behind me. So a screw is a kind of a lever. Okay. Now, inclined planes not only work with screws, but there's another place where you see an inclined plane, and that is anytime you move things apart. When you have a wedge, anytime you work with a wedge, you're working with a lever, and wedges appear all over in the world. What's the front of a knife? The working end of a knife is a wedge or an inclined plane. If you look at a chisel, what's the front end of a chisel? It's an inclined plane. If you look at a saw, what is a saw? A saw is, you look at each little tooth in a saw, each little tooth in a saw is a little chisel, nothing but a chisel. A saw works exactly on the principle of a chisel, and a chisel is an inclined plane. Of course, it works for big things too. If you look at the front of a plow that's cutting the earth, or the front end of a ship that's cutting the water, it's also a wedge or an inclined plane. Maybe it would be, I got an idea. Maybe what I should do is I should analyze a wedge itself. That's what I will do. I will analyze a wedge and show you how a wedge works. Now a wedge A wedge is certainly not a lever, but it works exactly like a lever. Maybe it is a lever. Here's the hammer. That's it. And there's the hammer, and down here is the wedge that you're going to drive into the log. And here's the hunk of wood. There it is. And there's the wedge going into it. You want to. Now the point of the whole thing is, of course, the hammer is hitting down. You're exerting a certain force down. But what you desire to do is to split this log. That's what you desire the wedge to do, to break this thing apart. In fact, if you were Superman, you wouldn't monkey with this thing at all. You wouldn't worry about pushing anything in. You'd just pull the darn thing. You just pull the darn thing apart. That's what you would do. But you're not strong enough to do it, so you do it in this roundabout way. Now, supposing you hit this thing again with a certain force up here of, say, 10 pounds. Of course, you might be able to hit a lot harder than that. But let's just, for the hell of it, say you hit with 10 pounds. What I want to know is, what is the force that's pushing the thing apart? Okay, how can I find that out? Well, I have to know something about my wedge. And again, let me say something about the wedge. Let's say that the wedge is, again, just to grab some numbers, let's say that the wedge is 1 foot long, and let's say that it's 1 inch wide on top. 1 inch. It's 1 inch wide on top. That defines the wedge. What does that mean? What does that mean? That means that if the wedge is entirely out of the wood's okay. But if I push the wedge in 1 whole foot, have I pushed the wood a foot apart? Oh no, if I push the wedge in 1 whole foot, I have only pushed the wood apart 1 inch. So here's a machine where one end moves a lot. The wedge moves all the way in 1 foot and only pushes the wood apart 1 inch. Of course, the motions are in the ratio of 12 to 1. And now which side moved a little? Well, it was the wood that moved apart a little, and the hammer that pushed this wedge down moved it down a foot. The wood moved apart 1 inch. So the small motion was parting the wood. The motions are in the ratio of 12 to 1. So I have to say that if I hit it with 10 pounds, there's 12 times as many pounds pushing the thing apart. So 10 times 12 is what? 120 pounds. 120 pounds pushing the wood apart. Now, if you stop and you begin to think about this, or one way you can either think about it or else you can tell it to somebody else. And if you tell it to somebody else, maybe they'll ask you a question. They'll think about it. They'll say, well, look, this analysis is kind of not realistic because, look, very often the darn thing splits before you get the whole 1 foot in. Sometimes you get it halfway in, and then it splits. So you can't really say that it goes in 1 foot. Okay, let's analyze it for going in only half a foot and splitting. In that case, it would go in. How far would it go in? It would go in 6 inches. It would go in 6 inches. But how far apart would the wood be if it went in 6 inches? Well, it would only be halfway down the wedge, so it would only be half an inch apart. See, this is 1 inch on top. You go halfway down, it's half an inch. So you would move the wood half an inch apart while you push the wedge in 6 inches. So what's the ratio of 1/2 to 6? Well, the ratio of 1/2 to 6 is the same as the ratio of 1 to 12. So you see it's still in the ratio. It's still in the ratio of 1 to 12, even if it goes in halfway. Now, let's look at another question that a person might say. Look, you say, look, it's pushing on this side with 120 pounds. What's it pushing on this side? Also 120 pounds. It has to, whatever it pushes on one side, it has to push the same amount on the other side. You know that by symmetry. And you say, something's wrong because look, you're getting not 120 pounds out of it, you're getting 120 pounds out of it, so something is wrong. No, nothing is wrong. Because remember I said that the thing pushes 1 inch. it pushes an inch. But if we just look at it from the two sides, if we say, how far is this left-hand side pushing, this left 120 pounds? Is it pushing an inch? No. The left 120 pounds, as the thing goes all the way in, is only pushing half an inch. And the right 120 pounds is only pushing half an inch. And 1/2 an inch times 120 pounds plus 1/2 an inch times the other 120 pounds is equal to 1 inch times the full 120 pounds. So it's okay that it's pushing on both sides with 120 pounds. You're pushing on top of it with 10 pounds in the hammer, and of course the earth is probably also pushing up with 10 pounds to balance that hammer too. So here's a problem that doesn't look at all like a lever problem. It does. You don't see a lever there. And yet, mathematically, when we analyzed it, what we learned from the lever, we were able to apply to this problem. And in a way, this problem is a lever problem. And the wedge is a lever, even though it doesn't look like a lever. You begin to see inside. The mathematical analysis enables you to see inside of the animal itself. It reminds me of a shark, and there is a porpoise. And if you look at the outside of the shark and the outside of the porpoise, they look very much alike. But if you could look inside of the porpoise, you'd see that inside, a porpoise looks very much like a person or a mammal inside, whereas inside the shark does not look at all like the porpoise. It would look like some kind of a fish inside. And so it is that if you think in terms of the physical principles behind these levers and these door jams and these inclined planes, and look at the underlying physical principle, that's like looking inside of the porpoise, and it's this mathematical analysis. Though we haven't done any equations, we have been playing with mathematical ideas, and those enable you to look inside. Well, I want to show you some other things that don't look like wedges at all, or that don't look like levers, but indeed are levers. And here's one that I'm going to show you right here. First of all, maybe well, I don't even have to erase the blackboard to show it to you. This is something that you will see in the world. And here it is. Pull on this thing here, and up comes the weight. These things it's called a block and tackle, but the name isn't important. The important thing is that it enables me to lift a heavy weight. You see, here's a weight. Am I using more or less force than the weight to lift it? Well, I use these things to lift motors out of automobiles. Obviously, I'm using less force. I wouldn't go through all the trouble to get this hardware if I was using more force. So this is a thing that enables me to lift this weight and lift it with less force. Now, of course, you know the question I'm going to ask you. Well, if this thing weighs 100 pounds, pretend it weighs 100 pounds, how many pounds of force am I using to lift it? And of course, holy cow, say this is a complicated machine. You'll ask me, how many wheels are up here? And there are 3. And how many wheels are down here? And there are 2. And we could get into analyzing this thing in a very complicated way. But the principle of work, the beauty of the principle of work is it enables you to see through it fast. Now I'm going to show you how to see through this machine fast using the principle of work. Here is a machine, and here is a machine where one end moves a lot and the other end moves a little, just like the wedge. The wedge moves a lot down and it separates the work a little bit. Now, which end moves a lot and which end moves a little here? Well, I pull this thing way down, all the way down to the weight. How far does the weight come up? Not very much. What's the reason for that? Well, when I pull off some string here, when I pull off a piece of string here, where does that string come from? This string that I pull off comes from here. It comes from over here. How many strings are over here? Well, let's count them. 1, 2, 3, 4, 5. There are 5 separate lines that go down to the weight. So if I pull a foot off of here, what must come from each of these lines in order to make a foot? See, they all stay equal, so each of them must give me 1/5 of a foot, because 5/5 of a foot is a foot. So if I pull this thing up, I pull out here a certain amount, say I pull out a yard of material here, each one of these gets shortened by 1/5 of a yard. So how far does this thing come up? It comes up 1/5 of the distance that I pull. In other words, my arm moves 5 times as much as that weight does. Going up or down, it doesn't matter, going up or down. However far my hand moves, the weight only moves 1/5 as far. Well, right away we can apply the principle of work. All the work that I do goes into the weight. It's not being eaten here by anything that's energy hungry. So all the work I do goes into the weight, and so the weight only moves 1/5 as much. So how could all the work go into the weight? All the work goes into the weight because the force on the weight has to be 5 times as much as the force on my hand. So if I pull with 1 pound, there's 5 pounds pulling up here. Or if this thing weighs 100 pounds, there's only 1/5 of 100 pounds on my hand. 1/5 of 100 pounds, what's that? 20 pounds. And that's the way the thing works. Now, when you understand a new idea, and you're using, it's a new idea, and you're also using a new principle, the principle of work is new to you as we apply it here, you should try to understand a thing another way. It's always important to understand a thing in 2 separate ways. You know, if you can only understand a thing one way, it's like touching a thing with 1 finger. All you can do is touch it with a finger. But if you can understand a thing 2 ways, it's like having 2 fingers. And when you have 2 fingers, of course, you don't just touch a thing. When you have 2 fingers, you can pick it up and manipulate it and grab it. So I want to show you a second way to understand this thing. And here's the second way to understand it. Let's begin our analysis of the thing by following this string up. And this string goes up and goes over the first wheel. I'm holding it here, and it goes over the first wheel. And here's the wheel, and here's the string coming up from my hand down here, and it goes over here and like this and goes down here. Of course, it's going to go through a very complicated trip down here, but it just goes over this wheel. Now we have to make one assumption. Let's assume that the wheel is frictionless. It's not really frictionless, but it's pretty close. Now, I want to ask you, if I'm pulling, and there's 1 pound of force on this string over here, that's this string here, how many pounds of force are pulling over here on this side, Well, let's see. I have 1 pound pulling this way. If I had 2 pounds pulling this way, then the thing would take off in that direction, so it can't be 2 pounds. If I put over here 1/2 pound, well, then I'd have the bigger force here, so it would go towards me. But if the thing stays exactly in balance, and you notice it's not moving clockwise or counterclockwise, it's moving no way, then if there's 1 pound of force of tension here in the string, when you get to the other side, there must be 1 pound here. So if I'm pulling with a certain force of 1 pound here on me, then the tension in this line is also, on this side, is also 1 pound. And then it goes around this wheel down here, the wheel down here. When it goes around the first wheel here, what happens? Well, it's the same thing. It's a wheel. Whatever tension is on this side must be on this side. So there's 1 pound tension in this string. And we go around this wheel here. And again, there's same on both sides, so there's still 1 pound over here. In fact, each time we go around, it stays to 1 pound. Now, so we know that the tension, whatever tension is on this string in my hand, it's the same tension all the way down to the end. Well, how many strings are pulling on me? 1 pound of tension. How many strings are pulling on the weight? Well, count them. We did before. 1, 2, 3, 4, 5. So there's 5 pounds. So whatever the force on me is, the force on the weight is 5 times as much. I do this, of course, we came to the same conclusion, but as I say, it's very important to try to come to the same conclusion in 2 separate ways if you possibly can. Well, it didn't look much like a lever, did it? But nonetheless, it's a lever in disguise. You see, as it says in the Bible, the lever has many guises. The devil has many guises, and the lever has many guises too. In fact, I'm going to show you another guise. This looks sort of like the devil, doesn't it? The syringes. I'll tell you, let's play with these things and see what we got here. Here I have 2 syringes. And they could be full of liquid or they could be full of air. And it works better when they're full of liquid, but it's less messy when they're full of air. So, but the difference is that you notice that one of the syringes is fat. This one over here is fat. And this syringe is not as fat. We'll call this one the skinny syringe, and this is the fat syringe. Now, they're connected. Usually they'd have a needle on the end, but took the needle off. And I didn't get my free needle here to put on the end, so we don't have any needles here. But they're connected with a rubber hose, and the hose is wide open, so there's no obstruction in the hose. If there's some liquid in here, and I push this one down, it'll go over to the other one. So let's watch what happens. If I push down this one, I'm going to push it down, and lo and behold, that one comes up. That's not any surprise. And now, of course, if I push this one down, that one comes up, which is just what you'd expect, because when I push one down, the stuff goes through the hose and comes out the other. And there it is. Kind of a nice play toy. But you remember that, as you can see, you don't have to remember anything, you can see it, that the syringe on this syringe is fat, and this syringe is skinny. Now, supposing that I do this. I push down on both of them so that neither one moves. I don't want to break them. I could push down so hard I'd burst the hose, but I don't want to do that. I just push down. Now, neither one's moving, but I'm pushing hard on both of them. Now, the question I want to put to you, am I pushing equally hard on both of them, or am I pushing harder on one than the other? Am I pushing harder on the big syringe, or am I pushing harder on the little syringe? Or since they're balancing each other, maybe I'm pushing equally hard on each of them. How are you to answer this? This is certainly, doesn't seem to be a lever, and we haven't talked about hydraulics or fluid mechanics or aerodynamics or syringes. We haven't talked about this at all. How can I expect you to answer this? But I can expect you to answer it, and you should answer it. And the answer is that this is a lever in my hand. How does it work? Okay, well, of course, you might think, gee, maybe which one do you really think I push hardest down on? I know I've asked many a class this question, and the class will always answer. The majority of the opinion of the class is always that the biggest force is on the little syringe. In other words, they think I'm pushing harder on this one over here. In reality, when I pass the thing around, everybody's kind of amazed that I'm actually pushing harder on this one. I'm pushing about twice as hard on this one. That's the answer. But of course, the answer is worth nothing. I don't give a darn about the answer. What I give a darn about is the story that leads to the answer, and that's what I'm going to tell you now. Why is it that the fat one I have to push down on twice as hard to balance the skinny one? Why is that? Okay, let's draw a picture of the syringes. Here's the fat syringe. And here's the skinny syringe. And there's a hose, a pipe that comes out of this one and goes over to that one. The pipe comes out of here, it goes over to that one. Now, here's the plunger inside the syringe. There's the plunger in that one, and there's the plunger in that one. Now the question, as I move this plunger forward, and I move it over to here, I squeeze stuff out of this one, isn't that right? I'll draw it simpler. Instead of drawing a realistic plunger, I'll draw a plunger like this, then you can see it better. And I will move the plunger forward over to this position, and I squeeze all this stuff out. Where does it go? It goes into the other syringe. Now this plunger here, if I move this one an inch forward, does this plunger move an inch backward? Heck no, because all this junk has to go into here. Can this junk fit into this space? No, because this is a skinny syringe. So if this one moves 1 inch, this one maybe has to move back 2 inches to accommodate so that all the stuff that's squeezed out of here can go into here. So right away you see that here we have a machine where when one piston moves 1 inch, the other piston has to move 2 inches. When this piston, the fat one, moves, oh, this is the fat one. When the fat one moves 1 inch down, the skinny one has to move 2 inches out. So here again is a machine where one end moves a little and the other end moves a lot. And of course now you know that this is a lever immediately when you hear that. And you know the rule that the end that moves a little has the big force, and the end that moves a lot has the small force, and the forces are in the ratio of the movement. So if the movement is 2 to 1 or 3 to 1 or 10 to 1, then the force is going to be in that ratio. Now, I know some of you are surprised, and when you're surprised, and again, when you get a result that's surprising, you should ask to see, can you explain this to me in another way? I'm really a little surprised that the large force was on the large piston and the small force was on the small piston. Can you explain this to me in another way besides using this abstract principle of work, force times distance? And I can. I will explain it to you in another way. Let me clean off the diagrams and just put the pistons in here parked. It doesn't matter where, they can be parked wherever they please. And there is some air in here, or water, I don't know what, but there's some stuff in here, and it's filling up the pipe and the tube, and it's filling up here. And as I squeeze down, I want to ask you, in which one is the pressure largest? Is the pressure largest here, or is the pressure largest here? When I push on these things, given that I'm balancing them, and you know I'm pressing harder on the big one, in which one is the pressure the greatest? Again, I've done this before many a class, and the class will always, knowing that this is the largest force, they'll say the pressure is largest in the right, and this one over here that I'm shaking. But that's not so. The pressure is the same in both of them, because look, they're connected by an open tube. If there was more pressure here than here, the thing go right? Of course, there's more pressure here than here, go back the other way. So you know the pressure has to be the same in both of them. We say, well, if the pressure is the same in both of them, how can the force be bigger here and the force be smaller here? Because what is pressure? How do you find out what is pressure? Well, you look on the automobile tire. What do you see on the automobile tire? It says 35 pounds per square inch. Pressure is a measure of the force that the gas or the liquid exerts on each square inch. Well, which piston has the most surface area? Which one of these things has the most square inches? Well, we can just take it out and look. There. Look, which one has most square inches? This one has more black surface area. This one has about half as much. So of course there's going to be, if there's 35 pounds or whatever the pressure is for each square inch, this one has more square inches for that force to work on than this one. So you're not at all surprised once you look into it that there's more force on this one. Of course, what are these things used for besides entertaining students? This is the basic principle of the hydraulic lever or the hydraulic jack. And if you go to a tool store, you'll see them. There'll be automobile jacks, and some of them will be filled with oil, and you pump, and what happens in a hydraulic jack is that the situation works like this. There is one end that's pushing up on the automobile and the other end that you're pushing on here, and you put a small force in here and you get a large force out of the other end. Another example of a hydraulic jack that you see, kind of spectacular, used to see these in the olden days in garages. They'd have a car, and here'd be the car up on the rack in an old-timey garage. And there's an old-time car, and there'd be a great silver piston that would come out of the floor. And the car would be lifted up on that great big silver piston. And underneath it, you could be darn sure that there's a fluid that's pushing up on that. And someplace way over in the side, of course, if you go over looking for it, the mechanic will think you're trying to steal his tools. But if you look over, you'll find there's a tube that comes out of the ground and comes way over. And someplace over in the corner of the room, there'll be a little piston with a pump working on it. And that little piston pushes on the big piston. And this is the little piston and the big piston. Small force here makes the big force here. Of course, this one goes back and forth a whole lot of times. and this one goes up. These things, incidentally, they don't work like this. They have valves on them so that this thing goes back and forth, and each time it pushes the fluid through and it can't get back again. That's how the practical ones work. Well, I'm going to leave you finally with a final question that I'll answer next time, it's the final lever question. And this is not hypocritical. This is an absolutely true story that I'm going to tell you. Years ago, when I took my first course in physics at the University of California, and I'd been there about maybe it was about 9 months into school. I'd finished my first physics course, and I took physics for physics majors. It's interesting how physics is taught. You know, if you take French, there's one French class, and it doesn't matter if you're a French major or if you're just taking it to fill some requirement and don't know anything at all about French, and in fact are handicapped at foreign languages. But everybody that takes French sits in that one French class, and they either sink or swim together. But in physics, there's 3 separate classes if you take your first course in physics. There's one physics class for non-physics majors that have a hard time with physics. It's called Physics 10 at the University of California. And then there's another physics called Physics 2A and 2B. That's for people who have to know a little physics, like doctors. It's reasonable a doctor should know a little physics, but the doctor can't be expected to understand calculus and all that. So they have this intermediate course in physics. And then for physics majors or math majors or engineers who have to know a lot of physics, they have another course, covers the same material as the first 2, but it covers it in an elegant mathematical way with calculus, and that's called what's that? Physics 4A, 4B, that's with level. It's very nice how the physicists break their courses down, but the French department won't have any mercy on the poor people. But at any rate, I was taking the Physics 4A course, and so I should be learning quite a bit, and I took it, and I came home, and my father asked me the following question. He asked me for help. This was not a make-believe quiz. This was actual, a true question. A flower pot had fallen on his client's head, and he knew to the weight of the flower pot and the distance that it fell, and he asked me to tell him the amount of force that it exerted on the client's head. Now, I like to make numbers nice and simple, so I'll pick some apocryphal numbers here that will make the thing nice and simple. We'll assume that the flower pot weighed 1 pound. That means that if we took the flower pot with the earth and the flower in it and put it on a scale, it would weigh 1 pound. And this flower pot fell a certain distance, striking the client square on the head. We won't monkey around with wind or anything like that. It's a square down hit. It fell a distance of 1 foot and struck the client on the head. And the question is, with how much force did it hit the client in the head? Now, would it be more than 1 pound or less than 1 pound? Well, you can kind of think. Would you rather have a flower pot set on your head, or would you rather have it dropped on your head from 1 foot above? So right away, you get the feeling that the answer is probably going to be some number that's more than 1 pound. And my father asked me to answer that question. And I'm going to ask you to answer it. How much force did it have when it hit the client's head? Now, I'm actually, when I ask you the question, I'm not asking for a numerical answer. I'm going to ask you a different slope on the question. And sometimes you have to ask yourself, remember I told you that when you have a question, it's a difficult question, sometimes you have to transform the question into your mind into another question. Here's the transformation that I'm asking for. I'm asking you, first of all, maybe you can solve the problem, and so one of you can actually give me the numerical answer that my father wanted. The thing hits your head with 5 pounds or 10 pounds or 100 pounds of force. Maybe you can actually know some equation that you can go through and figure out if a 1 pound flower pot falls 1 foot, how much force it exerts on the head. Maybe some of you can do it. That there are some of you that can't. And for those of you who can't, I want to ask you this. You say, well, I can't do it because, after all, I didn't take this fancy physics course that you took. You went and you studied calculus physics at the university, for one semester. You should have learned something, how to solve a simple problem like this. I can't solve the problem. But anybody who took a course intended for physics majors at the University of California and took that course for one semester or 1 year should be able to answer that question. Though I can't, I know it is an answerable question, and it is answerable at a reasonably low level of sophistication, such that the student might have that, which is incidentally what my father thought, that anybody who had gone to the university for one semester should be able to answer this question, taking a serious physics course. On the other hand, you might say that I should have been able to answer it. So, though you can't, you can say that I should be able to. Now, there's a third possibility, and that is that I can't answer the thing. The student who took physics for one semester, can't answer it, but a professor should. If there's somebody at the university that's the professor and he has a big government grant, or maybe even has a Nobel Prize in physics, that person should be able to answer the problem. Not the student who had taken physics for one semester, but a professor who was, a Nobel Prize professor should be able to answer that question. That's the third possibility. Now, the fourth possibility is that no one can answer. The question is unanswerable. In other words, as I define the question, I said a 1-pound flower pot falls 1 foot and hits the client in the head, that no one, not even a physicist with the Nobel Prize, can answer that. So that's the fourth possibility. Let me review them. Nobody, even Einstein, can answer the question. 2, a professor of great competence could answer it. Next, that a student who expected that he was a physics major after one semester of physics study should be able to answer the question. Or that I, who've watched Epstein lecture on levers, I can work it out. And here's the equation, or my method of working it out. I don't know if you use an equation, you probably use a little story, but I can work it out. So that's what I'm looking for. One of those 4 possibilities. Next time, we'll talk more about it.